Hi everyone, welcome back to Math 245. We are talking about combinations this week, and today this first lesson, lesson 30, is about how to find the number of subsets in a set when we're talking about combinations. So if we have a set that contains n distinct objects, it's very important that our objects are distinct here, then this set has 2 to the power of n, where n is the number of objects we have. It has that many subsets. And this number of subsets, 2 to the power of n, includes the empty set and the set itself, S. So we're going to do some examples to show that this is true. So, for example, a small pizza restaurant offers 6 pizza toppings. You can get as many toppings as you would like, and you can get any combination of toppings. So remember, with a combination, order does not matter. How many different pizzas are possible? Okay, well, I first want to determine how many pizzas come with no toppings, right? So I can get 0, 1, 2, 3, 4, 5, or 6 toppings. Now I need to determine how many pizzas I could get with each number of toppings. So how many pizzas with no toppings? Well, there is just one, right? Just a plain old cheese pizza. How many pizzas with one topping? So here I am choosing one topping from 6. So I have this expression, 6 choose 1. And remember, this is equal to 6 factorial over 5 factorial, 1 factorial. If you're confused as to where this expression comes from, I would check out our previous lesson. So this is equal to 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. That's 5 factorial, and then that 1 factorial is just the 1. So everything cancels except for the 6, which means that there are 6 different pizzas with 1 topping. That makes sense, right? Since there are 6 toppings. Okay, how many pizzas with 2 toppings? Well, this is 6 choose 2, or 6 factorial over 4 factorial, 2 factorial. So this will be 6 times 5 times 4 times 3 times 2 times 1 over 4 factorial, which is 4 times 3 times 2 times 1 times 2 factorial, 2 times 1. Let's see what cancels out here. So all of our 4, 3, 2, 1s cancel on the top and the bottom. And I am left with, on the top, 30, on the bottom, 2. So this is 15. There are 15 ways to choose a pizza with 2 toppings if I have a total of 6 toppings to choose from. What about 3 toppings? Okay, well, this is 6 choose 2, which is equal to 6 factorial over 3 factorial. What am I doing? Sorry. 6 choose 3. 6 factorial over 3 factorial times 3 factorial. So I have 6 times 5 times 4 times 3 times 2 times 1 over our first 3 factorial, 3 times 2 times 1, times our second 3 times 2 times 1. So this 3 times 2 times 1 will cancel, and then also 3 times 2 times 1 is 6. So I'll cancel the other 3 times 2 times 1 with the 6. So we're left with 20. And now it gets a little bit easier, and this is why. If I look at the expression 6 choose 4 for how many pizzas there are with 4 toppings, check it out. I get 6 choose 4 is equal to 6 factorial over 2 factorial 4 factorial, which is the same expression I got when I wanted to choose 2 toppings. So I already know this number. It's equal to 15. The reason that this is true is because choosing 2 toppings to go on your pizza is the same as choosing 2 toppings to not go on your pizza, or choosing 4 toppings. That's why choosing 2 toppings and choosing 4 toppings give us the same number of pizzas. It's the same with 5 toppings, right? So I'm running out of room here. But if I wanted to say 6 choose 5, this is 6 factorial over 1 factorial 5 factorial, which is the same as choosing 1 topping. So this is 6. Because choosing 1 topping to go on our pizza is the same as choosing 1 topping to not go on our pizza, which is choosing 5 toppings. And finally, how many pizzas with 6 toppings? Well, just 1. So now I have all the different numbers, every single combination, 0, 1, 2, 3, 4, 5, or 6 toppings. So how many total pizzas are possible? Well, no toppings gave me 1 pizza. 1 topping was 6. 2 toppings was 15. 3 toppings was 20. 4 toppings was 15. 5 toppings was 6. And 6 toppings was 1. So if I take all of these and add them together, 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1, I get 64. And this is the same thing as 2 to the power of 6. That's what our theorem up here tells me. A set that contains n distinct objects has 2 to the power of n subsets. So 64 is equal to 2 to the power of 6, where this 6 represents the number of possible toppings here. So this is kind of to show us where this theorem comes from. All right. In the next example, a souvenir shop sells 4 different postcards. How many different combinations of postcards can I purchase, given that I purchase at least 1 postcard? So we could go through this kind of pizza example again, right? What if I choose 1, 2, 3, or 4 different postcards? But I could also just use my theorem. So how many different combinations of postcards can I purchase? Well, I know that I have 4 total. So the number of combinations is simply 2 to the power of 4, which is equal to 16 different combinations. If you'd like, you can do this kind of problem using the method that we used in the pizza example, but our theorem here, that a set containing n distinct objects has 2 to the power of n subsets, sure does make it a lot easier. But I do think it was valuable to go through it with the pizza example to show us where that comes from. So, all right, this is the first of 2 lessons for today, so go on over to lesson 31. I'll see you there.